Okay guys, now we are going to talk about page table. Okay, so you have to know that a processor uses a page table to translate the virtual address to physical address, we know, and the page table contains an entry for each of the virtual page. There is an entry for the virtual page table. So this entry contains the physical page number and a valid bit. If the valid bit is 1, means the virtual page can map to the physical page. Otherwise, the virtual page is found on the hard drive. If the valid bit is 0, there is nothing there in the page table. Just every virtual page, we know there would be their corresponding page table entry would be there, and that page table entry would contain the physical page number and the valid bit. Okay, if the valid bit is 1, means what the virtual page you can map to its physical page. Otherwise, the virtual page is found where in the hard drive. Because the page table is so large, it is stored where it is stored in the physical memory. So you have to understand the page table maybe will be very hard, right? So what happened is that it will be very hard because page table is so large. So you have to store it in the physical memory. So the problem arises when you are storing it in the physical memory is that we know 2 times memory access would be there. Now let us assume that it is stored as a contiguous array. The page table contains a mapping of the memory system. Here if you see this figure 8.23, if you see here, the page table is indexed with virtual page number. Each of the virtual page number, that is the index the index would happen like 0, 1, 2, 3, 4, 5, 6, 7, then FFA, FFB, FFC, FFD, FFE, FFF, like that. Like virtual page number is basically number, and each of these virtual page have their corresponding entry here, and when the valid bit is 1, means it's present in the physical page. So that physical page number would be shown here. That is what you can see here. So the page table can be stored anywhere in the physical memory, you can store them. So the processor typically uses a dedicated register called as a page table register to store the base address of the page table in the physical memory. So we have to know that there would be a page table register which would store the base address of the page table, because we know the page table is stored in the memory. So to know that where exactly in the physical memory the page table is stored, there is a page table register which would store the base address of the page table. Base address means from which address onwards the page table is starting. So to perform a load or store, the processor must first translate this virtual address to physical address, then access the data, right? So the processor has to extract the virtual page number from the virtual address and add it with the page table register to find the physical address of the page table entry. So what happens is that first of all you have to understand the page table is stored anywhere in the physical memory. So that there is a page table register which would store the base address of the page table in the physical memory, so that whenever you need to access the page table using this base address of the page table, you can access this. So first, from the virtual address we will extract this virtual page number and we will add it with the page table register. So you will get the physical address of the page table entry. So how you get the physical address of the page table entry? I told you, we are going to add it, we are going to extract the virtual page number from the virtual address. From the virtual address you are going to take the virtual page number and you are going to add it with the page table register. Okay, and you're going to find the corresponding physical address. So finally you will get the corresponding physical address. Find physical address of the page table entry. So the processor then reads this page table entry from the physical memory to obtain the, so the processor now would read this page table entry would contain the physical address, right? When you're adding this, when you're extracting the virtual page number from the virtual address, you will get, and you're going to add it to the page table register, so you get the physical address of that page table entry that you can use to find the physical page number. If the entry is valid, means it can merges that physical page number with the page object, so you can create the physical address. This is how we are basically creating. Because the page table is stored in the physical memory, each load or store involves, we know, 2 memory access would be there. Okay, now using this you have to perform, using the page table, perform this address translation. Let us say the 32 bit, like that case it is. So C is what? C is 12, so it is 0011. You can write 7, you can write it as 111. 2 plus 4 is 6, right? So plus 1 you have to write. So that would be 7. Some lag in my system. I'm not able to write it right now. Okay. Now 4. 4 you can write it how? 4 you can write it as 0, 0, 0, 1, 0. 2 you can write it as 0, 1, 0, 1, 0, 0. Rest you are going to write it as all 0, completing the 31 bits. You will write rest all 0. Okay, so this is how you're going to write here. First 12 bits, that is the first 12 bit would be what? These would be the offset bit. So C74 would be my offset bit. Now the 2's corresponding page number you have to find. So 2 is here. So if I look the page table, this is my 2. The 2's corresponding is what? 0x7FF, right? FFF. That I have to add with my page offset, right? The page offset that I got, that I have to add with this page offset. So here if you see, this is my page offset 47C. So 47C I have added the 07FFF, as you can see here. So you get the final physical address. So how? This is my virtual page number 0x0002 and 47C. That page offset, 12-bit page offset would be the same, because 19 plus 12 when we do, you are getting 31 bits. So total there are 31 bits. Okay, so the 15 bit we will take, the next 15 bits would be from the page number that we will take. This is our page table. So valid bit and physical page number is there, and the index is the virtual page number. So in that virtual page number 0x7FFF you will take, and that would give us my physical address. Fine. So I told you 2 times we have to access the physical memory. So what happens here that you have to understand. So virtual memory would have a several performance impact if it required a page table read on every load or store, doubling the delay of load and store. So what happens, separate RAM access just to look up the page table is needed. So what happens is that every operation, because of that, every time 2 times when load and store and will come, along with the page table lookup and along with the memory access, 2 times you are accessing the memory. So what happens, the system becomes twice as long. Each operation would take now twice as long time here. So here page table, what happened, access have great temporal locality. Page table has temporal locality, means recently used things can be likely to be used again. So page table entries are no different. Like cache also, page table has temporal locality. So that means recently used page table entries, you can put it in a separate thing like cache, that is translation look aside buffer. That is why we use them. So the temporal and spatial locality of the data access and the large page size means that many consecutive loads or stores are likely to reference the same page. So that means we know large pages would be 4 KIB Android. So that means 4096 bytes can be there in one page if my page size is this many. So that means a typical program instruction or variable would be only just 4 bytes. That means 1000 consecutive access can all fall within the same page itself. So all requiring the exact same page table entry. So caching even a single translation is enormously valuable. So you are saying that most recently you can basically cache them. Why? Because most of the time one page itself, if you take, it can have 4 KIB size, that will be 4096 byte, and for a variable or instruction can be only 4 bytes long. So a lot of access can happen in one single page itself because of temporal and spatial locality. So because of that, if you cache at least one page if you cache also, that will be very enormously, they will be much more valuable. So that what happens here, what it is basically doing is that if the processor remembers the last page number entry that it reads, it can probably reuse this translation without reading the page table. So that is what the translation means. Remember the most recently used page translation, that is why use the TLB. We have already discussed about translation look aside buffer. So TLB you can access from the TLB within one clock cycle, approximately one clock cycle, and there is 99% of chances that whatever page table you are looking is present in the TLB itself, as we told, because of the temporal locality and spatial locality. So the process look aside to find the translation in the TLB before having to access the page table which is present in the physical memory. So in real programs and all, the vast majority of the access it happens in the TLB itself, avoiding the time to consume from the page table which is present in the physical memory. Understood? So now if I'm talking about TLB organization, a TLB organized as a fully associative cache. So how the TLB is organized? The organization is a fully associative cache. The number of entries in TLB 16 to 1512 itself, and the access time would be less than 1 cycle, and the hit rate would be greater than 99%. These are the things that you have to understand in the TLB. Okay, in the TLB you have to understand so here what happens is that a TLB is actually a fully associative organization. Okay, its organization is how fully associative, and the number of entries would be approximately like 16 to 51. The number of entries is actually very less. Okay, TLB is this is affordable because TLB is very affordable, you can say, because the TLB is very tiny. Only 16 to 512 entries are basically there. And access time in TLB is less than 1 cycle. Access time is less than 1 cycle, and hit rate is greater than 99%. Hit rate is very more. Hit rate is greater than 99% here, and you can see. So these are just the properties that you can remember. Now here if you see, each entry is essentially just one row of the page table, and a VPN paired with its VPN would be the paired with its PPN would be there, and a valid bit would be there. This is how the TLB what it is there. A TLB entry holds a virtual page number and its corresponding physical page number. The TLB is accessed using the virtual page number, indexed using this virtual page number. That is what means it is fully associative. 60 to 512 entries can be the right, 16 to 512, that's why it is kind of affordable. Access time would be less than 1 cycle. Hit rate is greater than 99%. Now TLB hit and TLB miss, we can talk about that. So PPN returned immediately if it is a TLB hit. So translation can be done under 1 cycle. TLB miss means what? TLB miss means it has to go to RAM, read the page table and get the PPN. Then we have to update the TLB again with this new entry for the future use. You have to update the TLB also. It is slow, but it is rare, because we told you most of the time, 99% of the time itself, you are going to get TLB hit itself. Now TLB is designed to be small enough that it can be accessed is less than 1 cycle. So you have to understand TLB is like so small. It has very small, like 16 to 512 entries only would be there. So that means it is very small. So that is why you can access them in less than 1 clock cycle. You can access them in less than 1 clock cycle itself. What happened? You can access them. Okay. So now here you see, without TLB, every memory operation has to take one page table RAM access as well as one data RAM access. It becomes 2 times slower. That is why we are using the TLB. Now let's do this example. We are doing this example using the TLB to perform the address translation here. Okay. So we are going to use 2 entry TLB. 2 entry TLB means that is 2 ways. In TLB there are 2 ways you can basically arrange the data. That is what 2 entry TLB means. So you are given some virtual addresses. Suppose the TLB has hold this valid translation of virtual pages 0x2. Suppose a TLB is currently holds valid translations of virtual pages 0x2 and 0x7 FD. And the virtual address which is given to us is 0x2 FC and 0x5 FB0 are the given to us. So 0x2 FC, if I am taken 0x2 valid translation is there in our TLB, right? So TLB hit can happen there. So here if you see from one figure which is 8.21, we can see in 0x2 and 0x7ffd's virtual physical pages we will take from the before table which is given in our text. Okay, so this, their offset is 47c. Okay, that is the 12 bits we are taking here, bottom 12 bits for, and 0x2's corresponding ppn is 0x7fff. So you are going to combine both of them, okay, by looking at the TLB. So TLB hit would happen here because in the TLB 0x2 is present, so TLB hit would happen here and you will get the physical address. But the next address if you take is this is FB0 is the offset, and 0x5's physical address we know, but that is present in the physical memory and not in the TLB. In the TLB that 0x5 value is not present, so you are not going to get that from. So you are going to load that page table entry from the physical RAM, and then you are going to, what you're going to do, take the VPN value and you're going to map that. What happens is that you're going to load this entry to the TLB also if it is required again, if you require it more. So here it becomes TLB miss would happen here. That is what you have to understand. Here TLB miss would happen, there TLB hit would happen. Understood? So here if you have 0x002 in the TLB, I told you it is a 2 entry TLB, that is entry 0 is here and entry 1 is the, this is what 2 entry TLB means. Entry 0 is the, entry 1 is the, so the given that virtual page number and their physical page number is given, another virtual page number and their physical page number is given. For us this is what basically is asked. Okay, so this physical page number, if I'm taking this multiplexer, then only you are going to get the physical. The offset would be same for both of them. Now we will see if whether this and this is giving a hit, or whether this virtual page number and this virtual page number is giving a, whether this virtual page number or whether this virtual page number is matching to this virtual page number, we will check. Then we will compare. Any one of them we will get a hit. Fine. And physical page number, that is the data path here, that we will take, we will get the multiplexer, we are going to take the physical page numbers here. Understood? So this is how it basically works. The TLB basically works here. So now let's understand about memory protection. An important reason to use virtual memory is to provide protection between concurrently running programs. Now there is another important reason why we are using the virtual memory, and that important reason is to provide protection. Because of this, an important reason to use the virtual memory is because it is providing the protection between concurrently running programs. So some programs would be running concurrently, so it provides protection. Who provides protection? The protection is provided by whom? The protection is provided by virtual memory. So virtual memory isn't just about creating an illusion of large memory. It also solves a critical security and stability problem, keeping programs isolated from each other. This is arguably just as important as memory size benefit. Apart from this, it can help in protection of our memory. That is helping the program, multiple programs to run concurrently. Right, keeping the program, so that means it actually provides protection when multiple programs are running concurrently. How? By keeping them isolated, keeping the programs isolated from each other. So it is solving a critical security and stability problem. That is what you have to understand. It is solving a critical security or stability problem. It is basically solving here. So virtual, so you have to understand that multiple programs are sharing the physical memory. What happens is the modern computers typically run several programs or processes at the same time. So all of the programs are simultaneously present in the physical memory. So when you run a browser or a music player or a text editor all at the same time, all these three programs have their data which is loaded at this RAM. So they coexist in the same hardware memory, just at different physical addresses. So in the physical RAM, you can see all of the modern computers, like they can run several programs or processes at the same time. So all of these programs would be simultaneously would be present in this physical memory. As you can see in the physical RAM, the program A, browser, the data, music player, text editor, OS kernel, that is the operating system. Okay, all of them are present simultaneously in our RAM. So So what happens is that the danger would be that no program should be able to access another program's memory without permission. Without protection, a buggy or malicious program could simply read or overwrite another program's memory. That means here, one program should not interfere with another program. If there is no protection, this can happen.